Let me click on that section 6.1 and get right to the section end where the exercises are and see what's happening with that conversion of radians into degrees, right? So let's see what problem did I ask you to do. I believe it's 47, right? So let us take a look at exercise 47 that deals with pi over 3, and instead of pi you can take 180, so you can divide 180 by 3, 180 degrees, and this will give us 60 degrees, and this is our result. So if you just put 60 in the chat, that's pretty good, and I think that pretty much, I think everyone did it right. That's a nice exercise. So the point is, you see pi, replace it with 180, and that's it. That's the idea. And if you go backwards from degrees to radians, then you're gonna, let's say, try problem number 39 with negative 60 degrees angle. So looks like that negative is gonna stay with us, and negative 60 degrees, how do you produce this radians? From, then you multiply it by pi over 180. So this is the way to do, and when you multiply it by pi over 180, you're going to return back to pi over 3, right? But with a negative sign in front. So this is going to be minus pi divided by 3. Just like that. So we have the way to convert, and I guess it's just good for practice to go back and forth with radians and degrees. I guess people feel more intuitive about degrees, because if you look at, say, 61.24 degrees, you right away get a feeling of what kind of angle it is, about 60 degrees, right? Pretty close to it. But if you turn this into radians, if you multiply it by pi over 180, you're gonna get some kind of number that you may not really feel very comfortable about. That's why it's good to be able to go from degrees and backwards, and that's the way to go. So if I tried one exercise here, let's say, how about problem number 63, that says, write this in radians. Well, similarly, doesn't really matter if you have a nice number like 60 or something like 125 degrees. We already know what to do. We multiply it by the fraction pi over 180, right? So this is how we do this. And for that matter, we need a calculator. So I'll go for the scientific calculator, that favorite Desmos. So in Google, I type scientific, choice 1 is called Desmos. And we go ahead and multiply 125 by pi. Pi is right here, where the square roots are in the same row. And then we divide this by 180. So we'll get 2 and something radians. So there's 2.181 radians. So that's some number that does not really tell us much what is happening. But if you look at the actual angle of 125 degrees, then you could probably right away imagine yourself on a unit circle, 90 degrees angle, with a little something, with what, 35, so it's like someplace here. But, and that one is, I guess, more intuitive to produce rather than this 2 and something radians. That's definitely not as clear, I guess. So that's the way we do these conversions, back and forth conversions. And I guess this is how this section should be done pretty much in all the exercises. I told you not to worry about the rest of the section, so technically you can skip problems starting at 71 because they actually give us some pre-calculus ideas, and I guess the book is called Pre-Calculus. So for trigonometry, I guess we can stop at this stage. Well, maybe later when we encounter analogous problems at the next chapters, we will concentrate on them a little bit better. So I guess it's time to finally move on to the next section, right? Let me go to the section 2 of chapter 6. And actually now we're going to produce new functions, so-called trigonometric functions. And those trigonometric functions are something that people think of in terms of sine function and a cosine function, sine and cosine. So first of all, how do we define these on the unit circle? So if I put a circle with radius 1, that's why it's called unit circle. So radius is 1. So no matter in what direction you put segment that touches the side of the circle, it's going to end up at 1. So I can take a look at the coordinates of any point on this circle, and coordinates are x and y coordinates, right? So we're gonna define this such as a x coordinate that deals with somehow angle that produces this nice little circle, so I can connect that point with a center, and that angle people call as t in here. So you can call it with any letter, but t is used because x and y will be taken as x and y coordinates of a point on this unit circle. So x coordinate I'm going to call as a cosine of t. It's just a definition, so don't need to ask me why. That's how they define it. Somebody says, why is this a table? Well, that's defined to be a table, not a chair, even though some people can sit on it, but table. And same with the sine and cosine. So we define, means we tell that we're going to call them with these symbols, and this is it. So x coordinate is a cosine of angle produced by taking a point and connecting it with a origin, and y coordinate is a sine. So sine and cosine of this angle t, or sometimes they use Greek letter theta. It's just like t, but in Greek. They really like those Greek letters in here. So if I go into take a look at these definitions, there's some more of them, but I think I just want to work on sine and cosine today. In fact, only on one, because we really want to get used to this instead of getting into the others. So I think these first sections of chapter, they contain quite a bit of information. They really packed with it. So what we can do is take a look at how they proposed to do some of the exercises here. So what I can do is actually take a look at the problems at the end of the section that just want me to find sines and cosines. So there are also other functions that I'm going to talk about next time, because I think it'd be overwhelming if I throw away on you so much of new stuff at once. So just sine and cosine. So as usual, I move to that group of exercises, which is called skill building. And I can start with exercise number 14, for example, because some people may not like number 13. But I'll start with 14. So we're in section 2 of chapter 6. So it's called 6.2. And I'm gonna take a look at problem number 13, which is going to be a pair square root 3 divided by 2 and 1/2. So there's two values are called x and y, right? So on this definition, we already know the cosine of angle, and we call it here as t, is going to be radical 3/2, and the y is going to be called as a sine of angle t. And this is it. And again, we define them to be like that. So let us see what kind of angle we're actually dealing with in here. So if I look at this unit circle, and if I try to find the, I said I do 14, but I actually do in 13. That's kind of odd. But anyways, 13, 14 doesn't matter. So I think 13 is even nicer. So if you look at this x coordinate, it's a radical 3/2. Notice that radical 3 is a little bit more than 1, so it's going to be someplace here, because that's a half, right? It's in the middle. So radical 3 is a little bit more than 1. And at the same time, if you discover the point on this circle with radius 1, unit circle, the y coordinate of that point has to be exactly equal to 1/2. So the point is someplace here. And we already know it's the sine and cosine for that little angle. And a good question will be, so what is this angle? And I think that's a very interesting question here that I'd like to discuss a little bit, because I already found the sine and cosine for this particular angle. They're just x and y coordinates, so there's really nothing to look for in here. But there is a little extra that I'd like to discuss. I'd like to actually find this angle. So there's some room here, and try to make this picture a little bit bigger so we can better see what is going on. So if I get this picture here, and notice that since my y coordinate is a half, then this will be a half for the side of this right triangle, because everything is perpendicular, right? Because they're coordinates of point, and we produce perpendiculars when we get coordinates. Now, this is a unit circle, so hypotenuse of this will be 1. And if I decide to actually attach another triangle of exact same size, so this is also going to be a half, then notice that what I'm going to end up with will be a triangle with equal sides, right? Because here we have a half and a half. So if I put them together, half and a half, is going to be 1. So we end up with equilateral triangle. And this enables us to notice that all angles of this triangle are going to be the same. They're all equal to 60 degrees, right? 60 degrees angles are here. And this actually means that our angle is exactly a half of that 60, right? Because the picture shows us that everything is cut in 2 pieces to produce that equilateral triangle. So angle T is 30 degrees. And this is a very useful observation for the future, turns out. In fact, after this, I can do problem number 14. And notice there is another angle analogous to 30 degrees will be utilized. So again, in exercise 14, right away, I can say that the x-coordinate of that point is my cosine function. So that's what we actually need to carry out of this. So x-coordinate, which is radical 3/2, right? That was the problem I tried to start with, but well, somehow I jumped to different one, but that's pretty much the same. So looks like I'm again doing this 13, 1/2. Sorry, I don't know what's going on with me. Why I can't do 14? Why does it bring me to 13 again? It's kind of odd. So sine of t is going to be a y-coordinate of that point. So the y-coordinate is negative square root 3/2. Okay, negative square root 3/2 is a sine. And then again, notice that if I try to put this on the picture with a point on the unit circle, then x-coordinate of it will be 1/2 for cosine, but y-coordinate of this point will be down below because it's negative square root 3/2. You see that? So 1/2 is here. That's x, and y they gave it to us, negative square root 3/2. So what kind of angle do we work with? Well, let's see how it is related with a previous exercise. So this is the point on circle, so I can connect it with the center, right? And looks like it is something kind of the same. So if I look at the previous problem, the angle was 30 degrees, but 1/2 was on the y-axis. Now 1/2 is on the x-axis. So if I take a look at this triangle here, it's also gonna have 30 degrees angle in it. Let me make it bigger so we better see this. Is not enough room. So I got a triangle here. And looks like 30 degrees angle will be the smaller one, because here we have 90, and that third angle will be 60, right? Notice that 90, I don't have to write, I just put this little box, and that automatically tells me that we have a 90 degrees angle. Okay, so then what? You say, why is it 60? Well, because remember, sum of all angles in any right triangle, 90 degrees triangle. And in this class, we'll be dealing with 90 degrees triangle pretty much all the time till the end, almost till the end. So if one angle is 60, the other is 30, and vice versa. Why one angle is 60? Well, because that's actually the same exact triangle. It's just kind of flipped and rotated since the measurements of its sides are the same, right? So what I just concluded was the fact that angle here that we care about, the angle is always one with positive direction of x-axis, is going to be negative 60 degrees. Negative 60 degrees. So I guess this is a good idea to think about over weekend, because we're going to deal with this 60 and 30 degrees angles all the time in this class. They be most popular angles, and they are associated with sides 1/2, and turns out square root 3/2. I say, Alex, why is it square root 3/2? Well, check with the Pythagorean theorem if you like to, because you know that a squared plus b squared is equal to square of hypotenuse, which is c squared. I hope you saw that. I think everybody saw it. It's been known for thousands of years, this Pythagorean theorem. So they say that hypotenuse is the longest side, c, and there's a and b here. So I'm gonna plug instead of c number 1, and if you put instead of side a this radical 3/2 squared, of course, and instead of b you put a half and also squared, well then what you're gonna get is a true statement, because when you square in your numerators, the square root 3 will disappear, so it's just gonna be 3/4, because 2 squared is 4. And then for the other number, it's a half. So when I square, numerator is still 1, but denominator 2 gives me 2 squared, which is also number 4. And I end up adding 3/4 with a quarter. And when I do this, I get 4/4 or 1. So it is working, and that's why we don't really need to always check. Just to be familiar with this number, square root 3/2 always goes with a half on the unit circle. The keywords here are unit circle, means that hypotenuse is equal to 1. See, that's important, because sometimes people just say, oh, unit circle, not unit circle. Well, the unit circle really is a big deal for all that. So this is something interesting to think of. And using the ideas of this square root 3/2 and a half that are being friends, I'm going to take a look at another popular angle. So those are friends of 30 degrees and 60 degrees, right? Unit triangle, or actually triangle with hypotenuse 1. So how about triangle with 45 degrees angle? Well, in this triangle, turns out when hypotenuse is 1, I can find the sides because they're the same. Because if you look at the other angle in this triangle, it's going to be the same as 45 as well, because their sum must be 90 when I add 45 and 45, and 90 degrees is also in that box. So what I'm going to do is use this Pythagorean theorem once again. So I'm going to treat one side as A, the other side also as A or B, right? A, B, and the hypotenuse is C. So I go ahead and utilize this Pythagorean statement. So we going to put, instead of A and B, the same numbers X. So it'd be X squared plus X squared. And this is the same as 1. 1 squared is 1. So now I need to find x. Well, we can solve a little equation here for x, and we see that x squared will be equal to 1 over 2. So when I find x, I'm gonna square root both sides. So I'm gonna just get x, and then I'm gonna need to square root 1 and square root 2, because I can square root numerator and denominator, and I get 1 over radical 2. Well, turns out they prefer not to have radicals in denominator. They prefer to make it be so-called rational denominator. So they put square root 2 and square root 2 here on the top and the bottom. And then what we're going to do is produce 4 in denominator. The whole point is, oh, sorry, square root 2 is square root 4. But square root 4 is just a 2. That carried away a little bit. So the 2, so no square root on the bottom, but the square root moved on the top. So I say, Alex, you know what? It's questionable. Is it better 1 over square root of 2, like you used to have, or radical 2 over 2? Well, in this book, they like 2 in denominator, not square root of 2. In fact, in all textbooks in trigonometry, it's the same story. So they prefer square root 2 over 2. And we'll see this number a lot, as well as the previous pair of values, which is a half and square root 3 over 2. So those will be with us all the time. And this will enable me to do problems like, say, 31 and so forth. So I'd like to take a look at the next group of problems. But again, I just want to deal with sines and cosines. With other functions, we're going to, of course, discuss a lot, but next time. So let me get a little room here, and I clean this side. So how about exercise number 31? So what they want to do is get so-called exact value, which means without a calculator, which means that it has to be with this square roots. Because it turns out that, yes, you can put this in the calculator and you will get some kind of decimal, but that's not what they want. They want these radicals to be present. Okay, we'll have them present. So I need to look at sine of 45 degrees. And also add it with cosine of 60. Okay, cosine of 60 degrees. So what I'm going to do is I'm going to now recall what happens here in the previous exercises. So looks like instead of cosine of 60, I already know what to utilize. Some like 1/2 and square root 3 over 2 story. So let us make those little pictures again of the unit circles and figure this out. So if I take 45 degrees angle, which breaks this into 2 equal pieces, we already know that the sides of this triangle are both the same, and they are both square root 2 over 2, right? Here and here. So I can say square root 2 over 2 for cosine, as well as square root 2 over 2 for the sine of angle 45 degrees. We just worked on them. So they want to know sine, so they want to know y coordinate. We also have x coordinate, but they just want to y. Okay, so we'll give them y. This is square root 2 over 2. So whenever we deal with 45 degrees angle and multiples of it, such as 3 times 45, 5 times 45, 7 times 45, because if you go 2 times 45, it's 90, so it's going to be not that. But odd multiples of 45 will give us these values. And then for the cosine of 60, I'm going to get the unit circle again. Otherwise, it's too messy on one of them only. So 60 degrees, how do I produce? Well, that's 30 and that. So I kind of break this into 3 equal pieces. Not kind of, I do break it into 3 pieces. And I take 2 of them. So it's 30 degrees each. So there's 30 and 30, 60. And I already know that one of them has to be 1/2. Remember, we just discussed this in the beginning of class. So 1/2 will be here. I say, Alex, how do you know it's here? Well, that value is definitely not 1/2. It's bigger than 1/2. So the smaller one is always going to be 1/2. Okay, very good. Very good. Thank you. So I think I already made the note for myself. So 1/2 is going to be here because one of them is always going to be like in the middle and the other will be pretty close to the top in this case. So it'll be square root 3/2, a big friend of 1/2. So what do we need? Cosine here. Okay, cosine is x coordinate. So cosine of 60 is 1/2, just like that. So this is just great. So I put the value of 1/2 to it and add 2 fractions with the same denominator. And this denominator is 2. So I go ahead and have square root of 2 and 1 added in numerator and still keep that same number 2 in my denominator. And yes, I can put this in a calculator and then some kind of decimal, but that's not what they want. They want those square roots. In fact, that's a standard way to produce the answers. So let me try one more. How about exercise number 32? So again, in this section, we looks like deal with angles that are either 45 or 30 or 60. Maybe with a negative signs, then what we can do is actually work them out. Oh, maybe instead of this degrees, I'll try one with radians for a change. I just saw there are some problems that have radians instead of degrees. Maybe I better try, where's the one with just sines and cosines? Do they have one or they have other functions only? I don't see. Okay, so maybe I'll just do number 32 because others will do next time. I think over weekend, the goal will be to get used to these 2 x and y coordinates, sine and cosine. So let me do number 32. That says, try to get sine of 30 degrees added with, actually subtracted with cosine of 45 degrees. So it looks like I could utilize the same exact ideas for the sines and cosines as in the previous exercise, right? Even pretty much same pictures, but now it's going to be a little different because we have 30 degrees angle, the little one. But we already know it's related to square root 3/2 and other one, which is 1/2. And I already can see that 1/2 is going to be right there. and the other coordinate is a square root 3 over 2. So what do we need here? Sine. Okay. Sine of this 30 degrees angle is 1/2. Well, then I'm going for the other one. So let me replace 30 degrees sine is 1/2, right? Because it's again y coordinate of that point. And it's always going to be like that. And that's a good thing about trigonometry class. So once you start to feel more and more comfortable about this, you'll notice you just do the same thing again and again and again. So 45-degree angle, our favorite. And then I will be looking at its x coordinate, right? And we already know that x and y are the same. Remember, they were both radical 2 over 2, right? Make sure that your denominator is 2. So square root 2 over 2, and the other one is also square root 2 over 2. So they're both the same, no matter if that's a sine or a cosine. So we're gonna take cosine for this problem. And, well, here we have, instead of cosine, we subtract radical 2 over 2. It looks like it's gonna be some negative number. Well, that's fine. Result could be positive, result could be negative. So we have minus, and then square root of 2 is here. Just like that. So be a good idea that you think about this over weekend. And now it looks like I could try something like problem number 27 here, because here we have radians. Last time we looked at the radians, so definitely should not forget about those. So we deal with a cosine of angle negative 3 pi over 2. So what is that? Well, I think it'd be a good idea to make a picture so we intuitively see what is going on. And the picture is always the same, unit circle. So in this class, I'll draw tons of unit circles for you. And then I'm going to need to get this angle, such as a pi over 2, 2 pi over 2, 3 pi over 2, with a negative sign, minus 3 pi over 2. So what I did, I just remembered that pi over 2 is same as 90 degrees. And that's the key idea to deal with all these multiples of pi's over 2. Why is it 90 degrees? Remember that pi was 180, right? All right, equals from now on, even though it is not exactly, but for convenience. So if pi is 180, and that's something that's good to remember, because 2 pi is 360. So then half of pi will be half of 180, which is 90. And since I go with a minus, I go in that clockwise direction, produce the point on the unit circle. Now this point has two coordinates. Y is equal to 1, and x is equal to 0, right? This is point with coordinates 0 for x, because if you draw perpendicular, you hit 0. And it sits at y-axis at point 1. So the coordinates are going to be x coordinate is cosine of this angle, and y coordinate will be sine of this angle, and y will be sine of that negative 3 pi over 2. So making the picture, I guess, is very good for the intuition into what happens. So we kind of overdone this exercise because we actually looked at not just cosine, but sine. I think this is interesting, right? So how about if I try one more for you, and then maybe you can try one, right? So the answer was here, 0, so it's 0. Let's try one more here with multiples of pi over 2. I think these are probably a little bit nicer. Yeah, that's very good. See, this is not obvious. That's the thing. To me, it took a while until I got used to these. And that's why I'm glad that you are thinking about them, because once you get it in one exercise, you get it for all exercises because it's all the same. And that's the good thing about trigonometry, but it sometimes takes a while to get used to it. So let me try number 22 exercise. In this problem, they ask to find the cosine of 7 pi. So it's multiples of pi. So what I do is, again, I'm going to make a picture of this. So I'm gonna get circle, unit circle, of course. And then starting at the positive direction of x-axis and going counterclockwise, I go 1 pi, 2 pi, 3 pi, 4 pi, 6 pi, 7 pi. So the actual angle happens to coincide with my x-axis. See, it's like a 0. Well, I guess so. Let's double check. 1, 2, 3, 4, 5, 6, 7. No, right, not. I should be careful. So it's 1, 2, 3, 4, 5, 6, 7. So it actually goes to here, right? See, because even number of pi's, like 2 pi, 4 pi, 6 pi, gives us 0, like. But odd number of pi rotations will give us here point on the circle. So as long as you found a point on the unit circle, then right away you know its coordinates. And looks like x is -1 and y is equal to 0. Because whenever you're on x-axis, the y coordinate is 0. And then I say that cosine is -1 because, once again, the definition that we saw today says that x coordinate is a cosine of that angle, whatever it is, happens to be 7. And now a little quiz for you from the same exact exercise. Can you tell me what is sine of 7 pi's? Sine of that 7 pi. And all you need is just recall definition of sine. Sine is y coordinate. So you just put this answer as usual in the chat, which is going to be always the way we do these quizzes. And after that, you can relax a little bit and start enjoying another weekend. Weekend is coming. Looks like they coming pretty fast. So make sure that you have a good time, relax, and look at these same problems that I did today, because I think those are good exercises. I tried to select the most common ones and just put the answer for a quiz here in the chat. And again, if you're not sure, if you're confused, well, you can think about it for longer and then send me that answer tomorrow or so. So that'd be fine. I guess I stop this recording here.